All right, what we are going to do today is just work a few problems in the frequency domain to review some of the concepts that we talked about before in our DC circuit analysis section. So the problems that we're going to work today, I have just taken from old tests because I think that's a fairly representative way for me to show you effectively what I expect you to be able to do. So the first problem that we're going to work is this guy. Where we have a time domain circuit containing a 50 ohm resistor, a 20 millifarad inductor, an 80 millihenry, 20 millifarad capacitor, 80 millihenry inductor. Got my components mixed up there, my apologies. Here I have a sinusoidal current source, which I'm going to call IS of t, and we'll define what value that has in a moment. I have a 24 ohm resistor here and a 30 millihenry inductor here. And I asked the students in years past to determine the following two quantities: the current Ix of t and the voltage Vy of t. If Is of t were given to be 18 cosine 35t plus 75 degrees amps. All right, so since this circuit is a time domain circuit, we need to convert it into the frequency domain by changing all of our voltages and currents into phasor voltages and currents, and changing all of our resistors, capacitors, and inductors into impedances. Okay. So I typically start with converting all of my voltages and currents into phasors. So I'm just going to draw my resistor, inductor, capacitor. Gosh, can't believe I'm getting that backwards again. So here's my circuit, and now we're going to convert it into the frequency domain, right? So the phasor representation of my current Is of t is going to be 18 angle 75 degrees amps, because all I need to do, since I have a cosine function, is keep the magnitude, keep the phase angle, and throw everything else away. While I'm at it, I'm going to express my quantities of interest as phasors. So I'll have a phasor voltage Vy and a phasor current Ix. And now all of my voltages and currents are expressed in terms of phasor quantities. The next thing that I do is I convert all of my resistors, capacitors, and inductors into equivalent impedances. I'm going to start with my resistors, where we know that the impedance of a resistor, ZR, is simply the resistor value itself. So that means this 50 ohm resistor on the left continues to be a 50 ohm resistor, and this 24 ohm resistor on the top right continues to be a 24 ohm resistor. So I don't have to do any actual work there. Next, I will take care of my inductors. So the impedance of an inductor, ZL, is given by J omega L, where in this case, omega is 35 radians per second. So let's call this inductor L1 and this guy over here inductor L2. ZL1 is going to be J times 35 times 80 times 10 to the minus 3, which I get to be J 14/5 of an ohm. For inductor L2, I'll have J times 35 times 30 times 10 to the minus 3, which I get to be J times 21 over 20 ohms. Lastly, I will make the conversion for my capacitor. The equation for a capacitor is 1 over J omega C, which is the same as negative J times 1 over omega C. So this is going to look like negative J times 1 over 35 times 20 times 10 to the minus 3, comes out to be negative J 10 over 7 ohms. So my circuit has been completely represented in the frequency domain now. So this is where we get to choose what type of analysis method we might want to use. Since Devarier was kind enough to suggest that we practice using current division, that's what we are going to use to analyze this circuit. Okay. So I'm actually going to redraw this circuit in a way that makes it more obvious that current division can be employed here. How I'm going to do that is I'm going to lump together these impedances that are connected in series. So effectively, I'm going to treat this 50 ohm resistor in series with this minus J 10/7 ohm capacitor as a single impedance, and I'm going to lump together this 24 ohm resistor and this J 21 over 20 ohm inductor as a single impedance. And so what that allows me to do is simplify my circuit to this, where I'm just using this box as a generic circuit element. This one on the left will have an impedance of 50 minus J 10 over 7 ohms. Then I have my inductor here, J14/5. I have my current source here in the middle, 18 angle 75 degrees amps. And then I have an impedance to the right. That is 24 plus J 21/20 ohms. We are now solving for this quantity Vy and this current Ix. I've redrawn the circuit in this way to make it very obvious that I have a current source in parallel with 3 impedances. So, and since I'm looking for the current flowing through one of those impedances, current division is a pretty straightforward way to figure out what that current Ix is. So, employing current division, I can say that my phasor current Ix is going to be my source current, 18 angle 75 degrees amps, multiplied by the ratio of 1/24 plus J 21/20 ohms divided by 1/50 minus J 10/7 ohms plus 1/J 14/5 of an ohm plus 1/24 plus J 21/20 ohms. If I throw this into my calculator, what I find is that Ix is equal to 2.060 with an angle of 152.747 degrees amps. And from this, I can say that my time domain quantity Ix of t is 2.060 cosine 35t plus 152.747 degrees amps. So we have practiced current division here. Once we know this current Ix, what's the easiest way for us to get our voltage Vy? Anybody have a suggestion? So Devarier has suggested KCL. I believe that I have a more simple route. So the way that I've drawn this circuit shows that all of the elements are connected in parallel, which means if we know or if we can figure out the voltage drop over any one of these impedances, we know the voltage drop over all of the impedances. So I would argue that the easiest way for us to determine Vy is simply to multiply Ix by the impedance 24 plus J 21/20. Because if we know the voltage drop, or the potential difference between this point and this point, that's the exact same points as Vy is measured at. So what we would get by multiplying Ix times the impedance 24 plus J 21 over 20 ohms is 49.499 with an angle of positive 155.252 degrees volts. And from here, we could say that Vx of t is simply equal to 49.499 cosine 35t plus 155.252 degrees volts. Now, this is not the only way that we could have worked this problem. This is just one particular way that I have chosen to work it to illustrate applying current division in the frequency domain. I'm not going to go through all of the steps for how we might solve it a different way, but I am going to kind of try to indicate a few things here. So I'm going to make a copy of this right here. And bring it to the next page. And now I'm going to follow Devarier's suggestion of using Kirchhoff's current law and show you how you might solve for this particular voltage Vy, because that's, to me, the other easiest possible way to do it. So we would be applying Kirchhoff's current law at the top middle node. We're going to be adding together this current plus this current plus this current plus this current with the assumption that our ground node down here at the bottom is our reference. So if we were to apply Kirchhoff's current law, as Devarier suggested, we would wind up having Vy over 50 minus J times 10/7 plus Vy over J 14/5 of an ohm minus 18 angle 75 degrees amps plus Vy over 24 plus J 21 over 20 ohms is equal to 0. And then we have a fairly simple and straightforward one equation, one unknown system that we can solve algebraically in 1 to 2 more steps. Another possible way to think about how we might solve for that if we solve for Vy that way first, then we can simply divide Vy by 24 plus J 21 over 20 to get the current Ix, right? So I'm suggesting here that Ix would simply be Vy over 24 plus J 21 over 20 ohms. Okay. Another way that we could solve this problem, calculating Vy first, would really just be to use Ohm's law. Recognizing that all 3 of these impedances are connected in parallel, we could say that Vy is equal to 18 angle 75 degrees amps multiplied by 1 over 1 over 50 minus j 10 over 7 plus 1 over j over 14/5 of an ohm plus 1 over 24 plus j 21 over 20 ohms, where this 1 over all this stuff is just those three impedances, the one I've circled in red in parallel with the one I've circled in green in parallel with that inductor, okay? So here in 20 minutes, we've talked about three entirely different ways that we could solve this circuit. So what I'm trying to reinforce here is that really any way that you're comfortable with will probably work on the problems that I have to give you. There might be some ways that are easier than others, as I've tried to illustrate here, but practically anything that you can throw at the problems I'll give you on your final exam should be able to stick and work. The only things that are going to be very difficult to employ would be a traditional nodal analysis or traditional mesh analysis technique. And the reason why those are going to be difficult is because your calculators can't solve the system of equations. Okay? I'm not going to give you any problems in the frequency domain that will require you to solve anything more than a one equation, one unknown system. All right, so let's take a look at another problem, unless anybody has a question about this one. Great. So the circuit that I'm about to draw is going to start off in the frequency domain. So let's say that we have the following circuit where we have a 15 angle 0 degrees volt source connected to a J1 ohm inductor, which is in turn connected to an 8 ohm resistor. And this is going to be terminal A. And then we have this path out here to the right that contains a 4 ohm resistor connected to a minus J5 ohm capacitor. And then we have a terminal B here. And our goal is to determine the Thevenin equivalent voltage, VTH, with positive reference at terminal A, and our Norton current where the direction is to the right. So there are multiple different ways that we could solve this circuit to get the two results that I'm looking for. But again, Devarier was kind enough to suggest that we review voltage division. So that's what I'm going to use to determine the Thevenin equivalent voltage. Okay. So with this circuit, our Thevenin equivalent voltage is going to be this voltage, positive polarity reference at terminal A, and it is the voltage drop over our open circuit. I'm going to call this voltage here VA, and this voltage here VB, such that my Thevenin voltage VTH can simply be expressed as the voltage VA minus the voltage VB. We are going to find VA and VB using voltage division. Okay. So I can say that my voltage VA is simply 15. Give me just a moment to save this and then restart this program, or this little menu is going to keep popping up over and over and over again. All right, sorry about that. So our voltage VA is going to be 15 angle 0 degrees volts multiplied by 8 ohms over J1 ohms plus 8 ohms, which comes out to be 14.884 angle negative 7.125 degrees volts. Similarly, my voltage VB is going to be 15 angle 0 degrees volts multiplied by minus J5 ohms divided by 4 ohms minus J5 ohms. And this comes out to be 11.713 with an angle of negative 38.660 degrees volts. If I substitute those numbers in to my equation for VTH up here, what I'll find is that my Thevenin voltage is 7.845 angle 44.215 degrees volts. So in this circuit, we've illustrated a pretty straightforward application of applying voltage division to get our two quantities of interest, which allowed us to solve for our Thevenin voltage in a pretty straightforward way. Obviously, there are other ways that it can be done, but I feel pretty strongly that this is a pretty simple and straightforward way to do it, probably the most simple and straightforward way to do this. Now, let's talk about I Norton. I'm going to make a copy of our original circuit. Put it down here, where our ultimate goal is to find the current I Norton that flows through this short circuit. I am of the opinion that you would be hard pressed to find a method to solve for I Norton directly that doesn't involve setting up a system of equations. We could do it. Actually, I think I just thought of one that wouldn't involve setting up a system of equations. So let me explain myself here. If I identified my nodes, so this is one node. This is a second node. And this is a third node. I argue that, let's call this voltage here, Vx. And let's call this thing right here ground. We could perform Kirchhoff's current law at node X and solve for voltage Vx. It's effectively the only unknown voltage in our circuit. So one application of KCL will give us Vx, and then we could apply KCL at the left-hand part of node X, so effectively at terminal A, or the right-hand part of node X, or effectively at terminal B, to determine our Norton current. So what I mean by that specifically is we could say that this current plus this current plus I Norton must equal 0, and we can express the current flowing up and the current flowing down in terms of that voltage Vx very easily. Or we could say this current plus this current plus I Norton is equal to 0, where we can express the current flowing down through the 4 ohm resistor in terms of Vx and the current flowing up through the minus J5 ohm capacitor in terms of Vx as well. But this is actually a very long way to do this problem. Can anybody think of what the easiest possible way to solve for our Norton current would be? Under the assumption that we know what our Thevenin equivalent voltage is. Find the Thevenin equivalent impedance. Absolutely correct, Barrier. For a problem that doesn't have any dependent sources, finding ZTH is going to be a straightforward thing, right? So if I wanted to find the Thevenin equivalent impedance, how might I go about doing that? Let's put a copy of our original circuit back here. Since the Thevenin equivalent impedance, which is taking the role of the Thevenin equivalent in resistance, requires us to have a dead network, I would turn off my voltage source by replacing it with a short circuit. And then I could simply identify my nodes. So I have this node, which I'm going to call C. I have this node, which is A. And I have this node, which is B. And I can see pretty easily, sorry, I went slightly too far, that this is A and this is B. I have to go, if I want to go from A to B, I have to go through C. And there are two different paths that I can take. One contains the J1 ohm inductor, and the other contains the 8 ohm resistor. Now I'm at node C, and to go from C to B, there are two paths that I can take. One contains the 4 ohm resistor, and one contains the minus J5 capacitor. So ZTH would simply be 8 ohms times J1 ohm over 8 plus J1 ohms plus 4 ohms times minus J5 ohms over 4 minus J5 ohms, which comes out to be 2.738 angle negative 20.670 degrees ohms. And then our Norton current would simply be VTH over ZTH, which is 2.865 with an angle of 64.885 degrees amps. So we've looked at this old test problem in a variety of different ways. Here, reinforcing how to do voltage division. We talked our way through effectively the modified nodal analysis technique that I introduced to you guys yesterday. We've looked at impedance combination. We've reminded ourselves that as long as we know 2 of the 3 quantities associated with Thevenin and Norton equivalent circuits, we can easily find the other one. What else do you guys want to listen to me talk about? All right, since no one is really chiming in with anything, I guess we are done for the day. So, oh, let me see what's going on here in chat. Problems with dependent sources. So, if I am being honest, Sydney, I typically don't actually include problems that contain dependent sources on your exams for this material. Now, I am more than happy to work problems that include dependent sources because we're just reinforcing simple, we are reinforcing the DC circuit analysis techniques that we learned at the beginning of the class. My biggest concern with working a problem using a dependent source would be we might wind up having to use nodal or mesh analysis, which would involve the use of a computer algebra solver, which I don't particularly have a problem with if you guys don't mind me popping MathCAD out here and working stuff. Give me just a moment to look through a textbook or something that I have next to me and see if I can find one. Just for the sake of argument. Yeah, I don't remember the last time I included a problem with a dependent source on the frequency domain analysis portion of the exam. Just because I find that keeping up with all the complex numbers is difficult enough without throwing those in the mix as well. All right, I believe I found one that we could conceivably work without the use of a computer algebra tool. So we'll take a crack at this guy. And I would like for you guys to help me out in guiding our analysis. So the problem that we're going to work is this one. Where we have a 2 ohm resistor in series with an 8 angle 45 degrees volt source. Here we have a J3 ohm inductor. This middle branch is going to contain a minus J1 ohm capacitor. And then we have a dependent source, 2 IC here. A 6 ohm resistor. And then IC is defined to be the current flowing down through the minus J1 ohm resistor. Now, obviously, we could throw mesh analysis at this and solve it in a pretty straightforward fashion if our goal is to solve for the quantity IC, but that would require the use of a computer. So instead, what we are going to do is we are going to get creative here. So the only way that I can think of that we could solve this without using or without setting up a system of equation containing multiple unknown quantities would be for us to do a source transformation on this practical voltage source, right? So we have a voltage source that is in series with a resistor. It does not particularly matter that it is a dependent voltage source in series with a resistor. Our rules will still apply. So if I perform a source transformation on that practical voltage source, what I will be left with is the following circuit. And I'm going to make a simple simplification here as well. So here's my 8 angle 45 degrees volt source. And because that 2 ohm resistor and that J3 ohm inductor are in series, I'm going to represent them with a single impedance having a value of 2 plus J3 ohms. Then I have my capacitor down here, which is minus J1 ohms. It's carrying my current IC that I'm trying to find. When I do my source transformation, so effectively what we've got here is voltage source in series with a resistor. This is going to turn into a current source. It should be a dependent current source, excuse me, in parallel with a resistor. So what I need to be careful about is I need to make sure that my resistor value stays the same. I need to make sure that I give my current source the correct direction. Since the positive polarity terminal is on bottom, I'm saying that the current should be flowing down. And now I need to figure out what value my current source has. So using effectively just Ohm's law to remind us what to do, we know that voltage is equal to current times resistance. And so current is equal to voltage over resistance. Or in this case, since we're working in the frequency domain, let's use impedance specifically. Even though we're using a resistor value, it'll still be okay. So from this relationship, my current will be 2IC divided by 6, or 1/3 IC. That's connected between this node and this node, which is the same as this node and this node. So I'm going to have 1/3 IC here. And 6 ohms here. And let's see, what will I have to do now? I think the easiest thing to do would be our modified nodal analysis technique, where we're going to call this node down here our ground, and let's call this voltage up here Vx. So if we write our KCL equation, we would have Vx minus 8 angle 45 degrees volts over the impedance of 2 plus J3 ohms plus Vx over minus J1 ohm plus 1/3 IC, where IC is just Vx over minus J1 ohm plus Vx over 6 ohms is equal to 0. Now we have a one equation, one unknown system that we could solve for Vx. And since we know the relationship between Vx and IC, we're one step away from that. So I'm not going to go through the algebra here because I believe I've done that enough and you guys should be able to follow my thought process there. This problem that I've just worked here, setting things up took me, I don't know, 6 to 10 minutes, is much more difficult than anything I would actually give you on your exam. And we were able to do it in a pretty straightforward thought process here. I think the only thing that might not have been obvious to do was the source transformation at the very first step. But past that point, it's doing things that we're familiar with. Was that a reasonable example, including a dependent source, Sydney? No problem. Any other questions or anything? All right. Well, I'm going to let you go in just a moment, but I do want to mention something. We're actually one lecture ahead of where I had expected to be. I didn't look at my syllabus closely enough, and so I taught complex number review and sinusoidal review on the same day, because I typically wind up having to do that during a face-to-face quarter. But because this is the summer, I didn't take into account that I don't have to cancel class on any days because I don't have any industrial advisory board meetings or anything like that. So we are actually one lecture ahead. So what we're going to do on, or what I would like to do, and you guys can tell me otherwise, is I would like to just keep on with our current schedule, where all of the remaining lectures, and I believe there are only 3 or 4 of them, I think it might just be 3. We're going to cover those next week, and then we can utilize Monday of, let's see, that would be Monday, August 8th as a review day. And then your exam will be given on the 9th, 10th, 11th, and 12th. So you can just take it on Tuesday, Wednesday, Thursday, or Friday, either in the afternoon or in the evening, whatever you choose. And I will be available all that week to answer questions as well. So does that sound like a plan to you guys? Does anybody have a problem with us staying effectively one lecture ahead? All right, nobody's telling me that it sounds like a terrible idea, so that's the plan moving forward. We're going to start covering our steady state sinusoidal power topics next week, and effectively wrap up all the class material next Thursday. And then I'm available for review effectively anytime you want it for the entirety of the week that your final is up. So I hope you all have a great rest of your weekend, and I will see you on Monday.